All right, Precalculus lesson 12.3, infinite sequences and series. So this is 12.3, infinite sequences and series. So as you can probably tell by the title, these are sequences, lists of items, and series, the sum of the list of items that are infinite. There's an infinite number of items. That's what we're dealing with. Okay, so one thing that this lesson deals with, well, let's just say you have some sequence. Okay, let's just say we have a sequence like, how about like, I'll go with 1/3, comma 1/6, comma 1/9, comma 1/12, comma dot dot dot. Right. Now, one thing that can happen is these can be represented in terms of n, where it's just like, all right, so the first item or the first element, you would say n is 1, and then for the second one, n is 2, for the third one, n is 3, where n represents the number of term that you're on, which that's consistent with what we've done already, right? We've talked about finding the nth term or finding the sum of the nth term, or we've represented the fifth term as a sub 5, okay? Well, one thing that we're not quite dealing with yet, but we will pretty soon, is figuring out how to represent this in terms of n. And I'll give you some tips and stuff later on. But one thing that we can see here is we have, one's on top every time. So that would just be a 1 every time. And then what's going on the bottom? Well, the bottom is increasing by intervals of 3. Right, from 3 to 6, you're going up 3. From 6 to 9, you're going up 3. 9 to 12, you're going up 3. And that's a tip that we have a 3 times n going on. And so this would be represented as 1 over 3n. And so when n is 1, you have 1/3. When n is 2, you have 1/6. When n is 3, because you're on your third term, you have 1/9, etc. So this would be represented as sequence in terms of n. And so one thing that the lesson has here is, well, if we're dealing with an infinite sequence, then what we're finding is we are finding, it's like, well, is our sequence as we go farther and farther out, are the terms getting closer and closer to any particular value? And what the schmancier mathematical way of saying what we're finding there is we're finding the limit as n approaches infinity of, in this case, 1 over 3n. In other words, as n gets infinitely large, as we're dealing with an infinitely large term in this sequence, what is that term evaluating to be? Or at least what is it getting closer and closer to evaluating to be? Well, with this one, because we have 1 over 3 times an infinitely large number, this one, the limit would be 0. Whereas as we go out infinitely far, we are getting closer and closer and closer to approaching 0, right? But what if we had something like, if we grab something like this? What if we had the limit as n approaches infinity of 9n squared minus 87n plus 12 over 2n squared plus n minus 135. All right, well, you might recall from earlier, we have talked about how to evaluate limits like this. And yeah, when we're dealing with evaluating limit as, in this case, n approaches infinity, the slightly longer explanations we said, well, you could multiply the top and the bottom by 1 over the highest power of n that you have. So in this case, it'd be 1 over n squared over 1 over n squared. So I'm just multiplying by 1, which I can totally do. And if I multiply by something by 1, well, so what happens there? We're still evaluating the limit. We haven't figured out what it equals yet, so we need to rewrite limit as n approaches infinity. Then the first term, we get 9n squared over n squared, which is just 9. And then we have minus 87n over n squared, so that simplifies to 87 over n, plus 12 over n squared, all of that over 2, plus, well, n over n squared is going to be 1 over n, and then minus 135 over n squared. Now we ask ourselves, what happens to each term as n gets infinitely large? Well, 9, this one here, it doesn't even have an n, so it's not affected by what n equals. It doesn't care what n equals, it's just 9. 9 is 9. A constant is not affected. 87 over n, well, that approaches 0, because 87 over an infinitely large number is getting closer and closer to 0. 12 over n squared also approaches 0. 1 over n as n gets infinitely large also approaches 0. Negative 35 over n squared as n gets infinitely large also approaches 0. And what are we left with? We're left with just this 9 halves. So in other words, if you have some sequence, I'll go with yellow, some sequence that follows this pattern. Okay? So you plugged in, for the first term, you plugged in n equals 1 and simplified. That's the first term. Second term, plug in n equals 2 and simplify. And I'm not going to take the time to do this, but I think you get the gist of what's going on. Well, then what happens is, if we ask ourselves the question, okay, as we go out infinitely far in this sequence, is the sequence approaching a particular value? Are we getting closer and closer to some particular value for what the term is? And the answer here is yes. As we go infinitely far, the values are getting closer and closer and closer and closer to being 9 halves. Another way of looking at that is if we were to graph y equals this, but with x's, 9x squared minus 87x plus 12 over 2x squared plus x minus 135. And we said, as you go infinitely far to the right, is the graph going up, 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 up without bound, or down, down, down to down without bound, or approaching some finite particular y value? And the answer is yes, is approaching a finite particular y value. Which y value? 9 halves. Okay? All right, so you have some where it's evaluating limits like that. Let me know if you have any questions. Then we also have some where we are wanting to find what a repeating decimal equals as a fraction. But before we do that, we need to look at something that we have, and it's a formula for the sum of an infinite geometric series. So this is sum of an infinite geometric series. All right, so geometric series, that's where to go from one term to the next, we are multiplying by some common ratio. And so let's just say we have one where a sub 1, say a sub 1 is 1/2, and r is also 1/2. So we're starting out with the first term of 1/2, and then each term after that we cut in half. So the sequence here would be 1/2, comma, 1/4, comma, 1/8, comma, 1/16, comma, dot, dot, dot. Okay? Keeps on going forever. So that would be the sequence. The series would be the sum of those. So that would be 1/2 plus 1/4 plus 1/8 plus 1/16 plus dot, dot, dot. Now it might seem like, well, you're always adding something, and so it seems like it should be infinity for what this will add up to be. But check out what happens when I do a little drawing. Okay, I'm going to use this to draw a little draw. Let's draw a little rectangle here. And I don't want it white. Yeah, we'll go with the same blue color. Okay. So I'm going to start out with hold on a second. Went away. I forgot it would do a rectangle inside of a square, and I want something that's a little bit more of a square. Okay, we'll go with that. All right, so the first term is 1/2, right? So first we're going to shade half of this square. So this would be if we found the sum of just the first term is 1/2. But then if we add the next term, we're adding a quarter. Well, that would be like adding this, right? And then the next thing that we're adding is 1/8, which would be like adding this, half of the quarter that's left. And then next we're adding 1/16, which would be like adding this. And the next would be adding 1/32, which would be like adding this. And after that would be adding 1/64, which is like adding this. Next after that would be adding 1/128, which would be like adding this. Next after that would be adding 1/256, which would be like adding this. And what's happening is, if we ever stop adding, we're not quite going to shade the whole square. If we ever stop, we haven't quite shaded the whole square. But as long as we keep adding, we are getting closer and closer and closer to shading the entire square. And if we never stopped, then what have we come infinitely close to doing? We have come infinitely close to shading the entire square. And if you are infinitely close to a value, then you can, for all practical purposes, say that you are equal to that value. So in other words, we can say that 1/2 plus 1/4 plus 1/8 plus 1/16 plus ... Keep adding those forever. And what does that equal? Equals exactly 1. You're infinitely close to 1. All right, we have a formula for calculating the sum of an infinite geometric series. And there's one catch. It's that r must be less than 1. Really, say the absolute value of r must be less than 1. In other words, we need to have an r value that is between -1 and +1. Because as long as we're between -1 and +1, we are going to get each subsequent term is going to be smaller, smaller, smaller. It's going to be closer to 0, closer to 0, closer to 0. Okay? All right, so here's our formula. Our formula is that the sum of an infinite geometric series is a sub 1 divided by 1 minus r. Again, where absolute value of r is less than 1. Okay. Well, here's one thing that we can do with that. We can find, let's just say, represent... Well, I'll tell you what. Let's do what we just did. Super quick. What's a sub 1? 1/2. Over 1 minus what was r? Also 1/2. What is that but 1/2? 1 minus 1/2 is 1/2. Oops, I meant 1/2. 1/2 over 1/2. What's 1/2 over 1/2? 1. All right, let's do another one. Let's say represent 0.1471 as a, repeating as a fraction. 0.1471 repeating, so we have 0.1471, 1471, 1471, 1471, etc. Well, if we represent this or view this as a series, what do we have? Well, our first term is 1471 is what is this? Tenths, hundredths, thousandths, 10,000ths, right? Over 10,000 plus another 1471. But now we need the next 4 decimal places. So that would be 10,000. The next one would be 100,000, million, 10 million, 100 million, right? So over 0, 0, 0, 0, 0, 0, plus, and that keeps going on forever. All right, well, what's our first term? Our first term is this, a sub 1. What's the ratio? Oops, that was supposed to be, sorry, up here, 1471. My bad. I don't know why I totally wrote that down as a different number. All right, well, the R is 1 over, I want to be doing that in blue. I'm sorry. R is 1 over 10,000. It's always, because we're repeating at 4 decimal increments, it's 1 over whatever the 4th decimal place is. So in this case, the 4th decimal place is the 10,000th place. If we were repeating every 3 digits, then it would be 1 over 1,000. Every 2 digits, 1 over 10. Every 2 digits, 1 over 100. Every 1 digit, 1 over 10, because it would be the 10th place. Okay, well, that gives us the information that we need to find this. So we could say the sum is a sub 1, which is 1471 over 10,000 over 1 minus r, which is 1 over 10,000. Okay, so what do we get here? Well, that's 1471 over 10,000 over, if we do 1 over 1 minus 1 10,000ths, well, 1 we could represent as 10,000 10,000ths, and we take away 1 10,000th, and we're left with 999 10,000ths. Invert and multiply, and the 10,000ths cancel, and we're left with 1471 over 9,999. That would be representing this as a fraction. And you're actually more familiar with this than you might think, because what if we dealt with this same thing, but let's say we had instead 0.333, etc. Okay. You've accepted for a long time, I'm sure, that 1/3 is 0.3 repeating, or 0.3 repeating is 1/3. But what you're saying with that is you're saying that 3/10 plus 3/100 plus 3,000 plus ... that when you add up this infinite number of terms, that adds up to exactly 1/3. Let's check with the formula, though. So what do we have? We have 3/10 over 1 minus 1/10. What is that but 3/10 over 9/10? Invert and multiply, you get 3/9. What's 3/9 but 1/3? Interesting little side note here. What if we did with 0.9 repeating? 0.9 repeating. All right, well, first term is 9/10 over 1 minus the ratio, which is 1/10. What does that give us but 9/10 over 9/10? 9/10 over 9/10 is 1. In other words, 0.9 repeating is the same thing as 1. It equals 1. And that really does not set well with students sometimes, because, like, well, what about like 0.9, Like, you eventually have, if we did 1 minus zero point 0.9 repeating, you eventually have a 0 at the end. Or sorry, you eventually have a 1 at the end. It's like 0.00001, but just a lot more zeros. Like, well, no, not a lot more zeros, an infinite number of zeros, which means if there are an infinite number of zeros, then well, you never get to that 1 at the end. And so when you do 1 minus zero point 0.9 repeating, the difference between the two, mathematically speaking, is 0 because you never get to that 1 at the end as far as the difference is concerned because there are an infinite number of zeros before you get to it. Anyway, so that's that. You have some of these where you are given some kind of a sequence or a series, and you need to identify um, what R is first and be like, oh, that's geometric, and here's what R is, and go from there. But let me know if you have any questions. I'm just looking to make sure there's nothing else, and I don't think so. So yeah, hopefully you're good to go. Again, let me know if you have questions. All right, bye.